Earth feels like a permanent sanctuary, but the fossil record tells a very different story. 66 million years ago, a single massive asteroid impact entirely wiped out the dominant species on this planet. If a kinetic impact of that scale hit us today, human civilization would effectively end in an afternoon. Over geological timescales, these events are a recurring statistical risk. Space agencies are working to make humanity a multiplanetary species, a civilization-level backup. Looking at our immediate orbital neighbors, Venus is closer, but its surface is a 450 degrees Celsius acid bath that melts solid lead on contact. That leaves Mars as the only viable option. But reaching it requires a massive commitment. Because the planetary alignment needed for a return trip only occurs once every 26 months, there is no option for an immediate rescue or abort. Once a crew lands, they are committed to the Martian environment for years. While Earth provides a thick nitrogen-oxygen mix, Mars's atmosphere is 1% as dense and 95% poisonous carbon dioxide. That thin atmosphere provides almost no insulation. Winter surface temperatures drop to minus 125 degrees Celsius, a cold intense enough to freeze human blood solid. Unlike Earth, Mars lacks a global magnetic field. Without that shield, the surface is continuously bombarded by high-energy cosmic and solar radiation. Spending 1 year on the Martian surface exposes the human body to the equivalent of 8 years of Earth-level radiation. Over time, that exposure significantly increases the risk of cellular damage and cancer. Between the thin, toxic air, the extreme cold, and the relentless radiation, an unprotected human would lose consciousness in 15 seconds and die within 2 minutes. Transporting heavy steel and concrete millions of miles across the solar system is logistically and financially impossible. We cannot build a colony if every brick has to be mailed from Earth. The engineering solution relies on in situ resource utilization, or ISRU. The plan is to harvest Mars's own raw materials, the dust, the rocks, and the ice, to build the infrastructure on site. To deliver the heavy robotic equipment required for this, we need massive, fully reusable rockets. This prototype is designed to haul over 100 metric tons of load to Mars, drop off the construction units, and return to Earth to be used again, dramatically lowering the cost of the mission. Once they arrive, autonomous 3D printers will process the iron-rich Martian soil into building material. By digging several meters underground and printing habitats inside the crust, we can use the soil itself to block out radiation and provide a stable temperature for the crew. Surviving on Mars requires a total shift in how we think about cities. Instead of glass towers, our first permanent homes will likely be pressurized underground hubs built directly into the planet's geology. To sustain those hubs, we need water. Fortunately, Mars holds millions of cubic kilometers of frozen ice, both at the poles and trapped just a few meters beneath the soil surface. Automated mining rigs will drill into these ice deposits, heating the frozen material to extract liquid water, which is then purified for drinking and sanitation. This water is the foundation of the entire colony. Through electrolysis, we can split water molecules to generate breathable oxygen for the base and hydrogen to manufacture the liquid fuel needed for the return trip to Earth. Feeding a colony is the next hurdle. Because the Martian soil contains toxic chemicals called perchlorates, traditional farming in the ground is impossible. Instead, we will use soil-free hydroponics and aeroponics. By growing plants in nutrient-rich water under artificial LED light, we can produce fresh food in controlled domes. This isn't science fiction. NASA has already successfully grown vegetables like this aboard the International Space Station. Mastering these closed-loop systems, where water, air, and food are continuously recycled, is what separates a temporary research station from a permanent, thriving civilization. Over generations, these systems will change our biology. With only 38, eventually we may begin terraforming, the process of artificially heating the planet to thicken the atmosphere and melt the polar ice, potentially allowing humans to walk the surface without a suit. It sounds like a massive leap, but consider our history. In 1903, the Wright brothers managed a 12-second flight in a wooden glider. Only 66 years later, humans were walking on the moon. Technological progress is exponential, not linear. Mars is no longer just a distant red dot in the sky. It is the next chapter of the human story. We are the generation that will witness our first steps toward becoming a multi-planetary species.